significant amount of passion. It's occupied a lot of my attention for the last 2 decades. The study of Earth's aurora and more recently Jupiter's aurora. So tonight I'm going to share with you Jupiter's aurora. For those of you who do not know what the aurora is, I hope that you'll walk away tonight with a new appreciation of what this is. What it is light in the sky that's generated by energetic charged particles, electrons, bombarding the atmosphere, causing the atmosphere to glow. So this is just a Hubble Space Telescope image of Jupiter's aurora superposed on the planet itself. However, before we can get into Jupiter's aurora, it really is necessary that we go back to Earth and focus on what we know locally on our own planet. And what motivates my research of the aurora is not so much to learn just about Jupiter's aurora, but to go and learn about another system that is different from Earth and try and apply the physics, the general physics, in a way that we can better understand our own Earth aurora and the Earth space environment. So basically a lot of what our group does here at LASP in the Planetary Magnetospheres group is what we call comparative magnetospheric physics. Now, the aurora is not familiar to most of us because we don't see it often in Boulder. This shows that the aurora, these emissions that you see, are basically limited to the polar regions. Here's an image from space looking at these auroral emissions. Here, if you can see, here's North America, here's Alaska, and this is the northern polar cap. This is why we often, many people at least that live in Boulder or in mid latitudes, are not familiar with the aurora. I usually start these talks by getting a show of hands just to find out who has seen the aurora, just so I have a sense. Okay, let me check. That looks like a minority. Who hasn't seen the aurora? Okay. The next sequence of images, I just want to go through to give you a flavor of what these emissions look like. So make note of the forms that you see, the morphology, the rich variety that you see in the displays. Note the colors, the variations in colors, the different colors, and notice the boundaries, the very sharp lower boundaries that you see in these. The colors range from greens to reds to even blues. Typically reds at higher altitudes, greens are the dominant emission that you see in most aurora, and sometimes a purplish lower border to them seen at the very bottom of these curtains. This is the aurora looking straight up overhead. This is something that if you do see the aurora, say if you're in Minnesota, you would see the aurora on the distant horizon as a curtain. If you're in Fairbanks, Alaska, or say Fort Smith, Northwest Territories, and the aurora's overhead, this is what it might look like. One of the most fascinating things I've found is to view the aurora when there's other things in the way, like a cloud. It's very interesting to observe aurora through clouds. Very interesting forms. A lot of times you'll see these horseshoe shapes in the aurora as they bend, these westward traveling surges. Often snaking. These are very dynamic. For those of you who are in here before the talk started, I was playing a sequence of images. They were a string of still images, so they were time-lapse, of the aurora from Tromsø, Norway. So these things aren't just still, they're dynamic, and we'll get a sense of that a little bit later too. This is really one of my favorite images. It's just absolutely fascinating. And if you could be there, and I can't impress upon those of you who haven't seen the aurora, if the opportunity arises, take a hold of it. Even if it means going to the cold white north in February. Bring your warm clothing, I guarantee it will be worthwhile. So the aurora, because this is a polar phenomenon, the aurora has been an integral part of northern culture and a major part of their ancient legends. And so this includes Eskimos, Athabascan Indians, the Lapps, the Greenlanders, the Northwest Indian tribes. And the aurora was certainly mysterious, very mysterious to them. And this was sometimes seen as perhaps a fearful omen, or perhaps it was a warning from whoever in the heavens, fire in the air, battles happening in the sky, torchlit pathway to heaven where your ancestors reside. I borrowed this from a recent film, children's film, which I think most children have seen, Brother Bear. So contemporary children's films, we can thank Walt Disney for this, have introduced the aurora to any kids ages 5 through 12, I'm guessing right now. The story in this movie, the aurora is actually a very integral part. I'm not certain how they portrayed it, but kids now are certainly aware. Anybody who's seen this, I think you're seeing it more and more in film. The aurora is showing up. So where can I see the aurora? As I said, the north is best, but sometimes we see it as far south as Boulder. It has been seen in Boulder. And what this shows is the number of days per year where you can see aurora. So you can see where Fairbanks is located. 100 days of the year you may see aurora. If you live in Seattle, maybe 10 days a year. Boulder, 1 day a year, if you're lucky. Mexico City, 1 night in 10 years. Okay, so this is a statistical average. This is basically where you will see the aurora. When you do see the aurora in Boulder, it's typically not a green aurora like you saw in those images. Typically it's a sort of diffuse reddish glow. So how high is the aurora? This has been an interesting question. When you look into the ancient legends, the aurora was thought to come down to the ground and take up, it was the pathway to heaven, essentially. But in reality, the lower edge of the aurora here is at about 100 kilometers in altitude. Commercial jetliner flies at 10 kilometers in altitude. There's your ozone layer. So this is fairly high in altitude. Here's an image. I don't know if you can see it very well. Might help to dim the lights. This is taken from the space shuttle looking at the aurora. And you can see actually you can't see the light. Let me just dim the light slightly. Does that help any? You can see the very large vertical extent here. And what you can't see, and I can see on my screen, is the red emissions are extending far above 300 kilometers in altitude. So of course, we need to do, without getting too technical, I want to give you a flavor of what causes the aurora. And in order to understand the cause of the aurora, we need to start at the sun, which is the source of the energy that fuels this phenomenon. And this is an image, you're looking close up at a big magnetic loop here on the sun, and these things can erupt and bulge out and make what we call coronal mass ejections. This is from the SOHO spacecraft. The sun is roughly this size in the image, and there's a disk here to mask the bright emission from the sun. And what you're seeing are these gases that are streaming away in these big blobs, if you will. These gases are ionized. That means it's what we call a plasma. It's a hot ionized gas, which means that it exists as charged particles, protons and electrons. And we call this gas that's streaming away from the sun the solar wind. So what happens when these supersonic flows coming from the sun encounter the Earth? Well, the Earth has fortunately got its own little protective barrier. If we look at the inside of the Earth, we notice that it contains basically 3 layers: a rock mantle, a liquid outer core, and a solid inner core. These are metallic: liquid iron and solid iron. And when you combine, the motions of these liquids, the liquid part of the core, it generates a magnetic field. And this magnetic field that it generates is what we call a dipole magnetic field. It would look like a field if you've ever done this in a classroom. You took a bar magnet and sprinkled iron filings around, you get these loopy patterns. So this is what the Earth has, and this turns out to be important. It's an important protective barrier from the solar wind. The reason it protects is that charged particles can't move across magnetic field lines. So they can't just charge in across this field line, they're forced to go up and around. So as a result, as the solar wind encounters the Earth, the magnetic field deflects the flow. This is supersonic flow, so it makes a bow shock here, and it generates another surface called a magnetopause, which reflects the shocked flow. The magnetic fields become stretched by the solar wind, so they're no longer just loops. They're loops on the front, they become stretched in the back like elastic bands. Imagine the solar wind grabbing these things and stretching them back. So now already you can imagine a way of loading energy into the system. So the solar wind interacts with what we call this cavity as a magnetosphere. This animation illustrates the whole process, starting with the coronal mass ejection, bursting forth from the surface of the sun, propagating towards the Earth, and this hot ionized gas then interacts with the magnetic field. It stretches it back, and it stretches it and stretches it until finally one of those elastic bands breaks and sends energy up into the polar region here and makes the aurora. This whole topic could be a seminar in its own, and I encourage anybody who would like more technical discussion of what you just saw there, feel free to hang around for a little while afterwards. So if you look at the aurora, again as imaged from space, the dark region in the middle, very loosely speaking, you can imagine what this is it paints a boundary between magnetic field lines, which are closed loops, and magnetic field lines which are open into the solar wind. And so that's generally what we see at Earth, is it delineates an open-closed boundary in the magnetic field topology. So the final issue that I want to address is what makes the colors in the aurora. And there's a lot of complicated physics here, but I want to at least give you a flavor of what's happening here. The Earth's upper atmosphere is made up of atomic oxygen, molecular nitrogen, and molecular oxygen. Because atomic oxygen is the lightest, it tends to float above everything else, the heavier molecules that are dominant at lower altitudes down here. This is 100 kilometers in altitude and 300, so this is the auroral region. And what happens is energetic electrons come streaming down the magnetic fields. These little pink things, they crash into these are atomic oxygen and cause them to glow. So in the 200 kilometer region, there's a red emission line in the oxygen. At lower altitudes, it excites a green emission line. And at very low altitudes, it excites this purplish, pinkish nitrogen, molecular nitrogen emission line. So you can imagine if these precipitating electrons, as we tend to call them, are showering down on the atmosphere. If they're not very energetic, they're not going to make it very deep into the atmosphere. And so you may just end up exciting these red emissions. The more energetic they become, then the deeper they can penetrate into the atmosphere and start to excite these other emission lines. Very energetic, very hard precipitation can then tap into making these pink emissions. So when you see a really good bright aurora, you typically see these pink, purpley lower borders on those curtains. One of the reasons why you don't see the green aurora if you're in Boulder observing the aurora is typically it's a soft precipitation that's just exciting these red oxygen lines at high altitude. So another animation here just to illustrate the process. So imagine that you're a solar wind or you're an electron which is streaming through and you somehow find yourself in the magnetosphere and caught on a magnetic field line. And you move down this magnetic field line and you're suddenly accelerated to very, very high speeds, about 1/10 the speed of light. you crash down into the Earth's atmosphere, and you begin to collide with atoms and molecules. Exciting these are the red oxygen emissions. You make it farther down because you're more energetic. Exciting green emission lines. And finally, these nitrogen emissions. So you might say, well, wait, these are both emission lines from oxygen. Why wouldn't you get green and red mixed together? Well, just to make a very long story short, the red emission line has a long lifetime. So when you hit the atom, it takes about 100 seconds before light is emitted. When you hit the green, it takes about a second before light is emitted. And so if you're in an environment where you're colliding with your neighbors frequently, say faster than 100, one collision per 100 seconds, then you're safe in your excited state and you can emit the light. If you collide, you can share your energy with your neighbor and there's no emission. So typically what happens is that red emission line can only exist if it's collisionless. So there's very few collisions. When you get deeper down, those emissions become interrupted, so to say, by the emissions, and you're only going to see the green. Okay, so let me digress here. How does somebody, by the way, I grew up in Boulder, Colorado. How does somebody like me, who grew up in Boulder, Colorado, who had never seen the aurora as a kid, become interested in the aurora? So what I'm going to do is just give you a quick summary of the journey that I made as a student through graduate school and how I ended up studying Jupiter's aurora. So I want to show you how I was motivated to get into the Jovian system. So usually there's got to be a catalyst. And most of us are quite affectionate of the outdoors. And obviously as a kid growing up here, I was very, very fond of our local mountains. I loved winter. I loved stories about the North, some fine children's literature out there. And so, of course, you can see where this leads. It leads to Minnesota. So I was an undergraduate at Carleton College in Minnesota, and this is where I saw my first aurora. I was taking an observational astronomy course, and generally you want to see the stars when you're taking observational astronomy, and unfortunately there were some nights where there was this ghastly glow in the sky which was screwing things up. Well, I learned from my astronomy professor that in fact one never ever complains when you see an aurora in Minnesota. That is a treat. So I learned about the aurora. Minnesota, it was cold. It was kind of that Jack London sort of esque experience. It wasn't really that extreme though, and there were no mountains. So you can see where this is leading. This is the approach into the Fairbanks International Airport, looking at the Alaska Range. Now this is more like intense cold, big mountains. This is the mountains directly south of Fairbanks. And of course Aurora, which I now knew about. I had seen it. It had been sort of a mystical something or other that I was aware of as a child. It had become a reality in Minnesota. And going to graduate school at the University of Alaska Fairbanks seemed very appealing to me. So I spent most of the 90s in Fairbanks. I studied physics, among other things. So one of the unique things about Fairbanks is you're located right there. So if you have the opportunity to study the aurora, how do you do it? The Poker Flat Research Range is located just outside of Fairbanks, and this is a NASA-operated small rocket research range. And they had a number of rocket-based experiments have been done with the aurora. And I actually wasn't initially directly involved with rocket experiments. I was involved with a satellite project, which I'll tell you about in a minute. But what I want to do is just show you sort of historically, how do you study the aurora when there's so much uncertainty up there? You see an emission due to electrons coming down a magnetic field line. What do you do to really explore that? And if you're a child with a magnet, a bar magnet, and iron filings, it's neat. You can see the whole magnetic field. You can trace field lines if you sprinkle the iron filings on. It all kind of comes to light. So somebody must have had a brilliant idea back in the 70s. They said, let's sprinkle iron filings on the Earth's magnetic field. But not iron filings. We need something that will trace the magnetic field, something that we can see and track with ground-based cameras. And it turns out that if you take solid barium and you detonate it and turn it into a gas, and it's exposed to sunlight, A, it ionizes, and B, it scatters sunlight resonantly. And it emits a very particular color. It's a green or purplish color. So if you detonate one of these things and you say tie it onto a rocket, send it up to an aurorally active region, and then detonate one of these so it squeezes like a tube of toothpaste and sends a stream up the magnetic field line, you can watch where these ions, the barium ions, go. So you have Aurora here, and you're watching what their fate is as they go up the field line. So this next image is from the Skylab barium experiment. And what you can see here are some streaks. And what's painted onto the image is an actual, it's basically the Earth's magnetic field line based on some simple modeling. And sure enough, you can see how it traces out the Earth's magnetic field. So now there's a way of actually going up and painting the sky. We can really bring this thing to life. We can see what on Earth is happening up there. And I think one of the most revealing experiments of this type was called the Limerick Experiments. This was done in 1982. And something very odd happened. And the difficulty of these experiments is you really want to be on an auroral field line. And so you're the PI of this rocket, and you're looking at all of the all-sky camera video data, and you're thinking, okay, oh, it's only $10 million if we miss it, but oh, should I push the button or not? So there's the Aurora, it's sitting there, it's sitting nice and still, but it takes about 15 minutes for my rocket to get there. Is it still going to be there? So there's a risk. And so a number of these experiments were done. This one was very successful. They launched the rocket, the Aurora stood firm, they got onto basically the magnetic field lines where these Aurora were active, and shot the barium up the field line. And up and up and up it went. This is 13, 14, 15, 16 minutes. And notice this is the bottom of the magnetic field line. This is going up in altitude. Mysteriously, this streak just stopped. And that caused some concern. It can't just stop. If it stopped, you'd think that there would be a pileup, and the density increase would mean it would glow brighter. That clearly isn't happening. So actually what's happening is the opposite. It went up the field line, and it reached a point where suddenly it was accelerated up. And so to conserve flux, if the particles start moving faster, then their density is lower, and hence there's less emission. And so what was inferred here is, in fact, right at this altitude was the point along the magnetic field where the electrons are being accelerated downward. And this was a very, very important experiment. It revealed basically the spot on the Earth's magnetic field line where the acceleration of the electrons takes place, and that's roughly 1 Earth radius in altitude, 6,000 to 8,000 kilometers in altitude. There's some point where waves can propagate along the field line, but at that point electrons become accelerated. Electrons will be accelerated down by an electric field, ions are accelerated up. And so that's why this stream just stopped. So these are the sorts of experiments that were being done. When I came to graduate school, I arrived just in the midst of the CRESS mission. CRESS stands for the Combined Release and Radiation Effects Satellite. I was part of the release side of this. This satellite was built here at Ball Aerospace in Boulder, by the way. And I actually saw it before it was launched, not knowing that I would later become involved with it. These releases, so they're done from a satellite now, so they're traveling at much higher velocities. And the purpose of the experiment was simply to blow up a cloud of gas that's just moving perpendicular to the magnetic field and watch what happens. And so you start with neutrals and you form this ion trail in the wake here. And I'm not going to go into all the physics of why we're interested in this, but out of this came a proposed experiment. And the experiment was, if you throw plasma against a magnetic field line, you can imagine what it does is it's like a guitar string. You twang it. And so this thing starts vibrating. And the same waves that we think generate the aurora should be generated by this cloud. And those waves could generate electron acceleration and make an artificial auroral spot. So this is a proposed experiment. This was never done. And at the time, I actually wrote a proposal to try and to get after some of this physics. But then something else happened. I was introduced to John Clark from Boston University. And John Clark is an expert on imaging Jupiter's aurora with the Hubble Space Telescope. And it turns out that Jupiter's got its own naturally occurring artificial plasma injection experiment, and it's called Io. It's the innermost of the 4 Galilean satellites. So Io is located at 6 RJ planetary radii from Jupiter, and it's embedded in this funny torus of gas. This is it's ionized. There's both some neutrals. Neutral gases are meant to be represented by the yellow here, and then everything in red is ionized. And the funny thing is because it's embedded in this torus of gas, this is a schematic showing Io, and it's showing the flow of this gas, the plasma, around Io. And when the plasma collides, so this thing has an atmosphere. It's by the way, the most volcanically active obstacle object in the solar system. So it collides with this atmosphere, and the net result is it generates a huge current. 3 million amps of electric currents, which diverge and flow along the magnetic field lines toward Jupiter. So this thing is generating, a huge amount of power associated with this, like terawatts, very large number. And so if you go and look at the auroral video here from the Hubble Space Telescope, you see this interesting spot here, a long stream, a long wake behind it. It turns out that if you map the magnetic field from that spot, it would map straight to Io. So this is an aurora that's associated somehow with the moon, Io, and somehow with this huge current that's generated due to the interaction that it has with the gases in the magnetosphere. So for me, I thought, well, why bother doing these artificial experiments when we've got one occurring naturally in the solar system? Let's go and understand this. One of the grand challenges of trying to understanding Earth's aurora is we can see the emission that comes out, but we really don't understand where in the magnetosphere or what in the magnetosphere is driving it. What's the source of energy? What's the flow of energy from that source to the ultimate emission? What's beautiful about this system is it's somewhat closed. We understand the source of energy, and we can look up and we can see the emission. And we can try and understand the physics of the coupling between the two. So this is really what diverted my attention away from the Earth and got me very interested in Jupiter's magnetosphere and its aurora. More about plural aurora in a minute. But let's step back. What about the rest of the aurora you saw in that image? So Jupiter, like Earth, has got a dipole magnetic field, but it points the opposite direction. So these field lines point from north to south, whereas Earth points the other way around. The magnetic field is very strong, about 20,000 times stronger. And of course, this is now a schematic of what its magnetosphere would look like. And if I could put Earth's diminutive little magnetosphere in Jupiter's magnetosphere, it would fit in that little box there. This is an enormous, enormous beast, due in part to the very strong magnetic field, but also due to the plasma source from the moon Io. So I talked about this gas cloud that's circulating around Io. That is due to material that's come from the moon. So the distance from the planet to what we call the magnetopause is about 100 Jupiter radii, and you could fit about 1,000 suns inside of Jupiter's magnetosphere. So the Io plasma torus, you can actually see it glows in the ultraviolet very nicely. So when the Cassini spacecraft goes toward Saturn, and some of you may be familiar that Cassini is currently orbiting Saturn and collecting radidata of the Saturnian system, when it flew past Jupiter, it gathered this nice data set of the UV emissions coming from the torus. And here you can see the torus wobbling because the magnetic dipole is tilted. So the plasma likes to organize itself on that magnetic field, so as the planet rotates, it wobbles like a donut. So the total mass in this torus is about 2 megatons, and that's due to the source of about a ton per second coming off the moon. As this plasma circulates through the magnetosphere, so you can imagine as the planet spins, the magnetic field moves with it and the plasma with it as well. It's swirling around, and the temptation or the tendency of this plasma is to want to move upward. Just as when you're driving in the car and you take a turn, you tend to want to go straight. This fictitious centrifugal force that the plasma experiences really causes it to want to move radially outwards, and as it does so, it drags the magnetic field with it. So the problem is Jupiter wants to hang on to its plasma. It's very possessive, and it wants to keep it rotating, which means that as the plasma moves radially outwards, momentum must be transferred to it to keep it rotating with the plasma, with the planet. And so the ensuing battle that occurs involves significant currents, which now flow along the magnetic fields, to try to extract momentum from the planet, and give it to the plasma as it moves out here. So one could imagine as an analogy these magnetic field lines like copper wires. They're able to carry a certain amount of current, but if I really hooked up a hefty source to it, you could imagine I could at some point melt these copper wires. They're just not going to be able to carry the current that I'm asking. And the same sort of thing is going to happen to Jupiter. More and more and more current is being demanded to try and keep this plasma moving, and eventually something snaps. And it snaps somewhere up in here, kind of like where I told you we were accelerating the electrons at Earth at about a planet radius above the surface. So somewhere up in here, something snaps, and it can't hang on to that plasma anymore. And what you see is the plasma was co-rotating, but now suddenly there's a departure from co-rotation. It's no longer rigidly co-rotating, and it is exactly at that point that Jupiter's main auroral oval maps to. This is very different from Earth. So let me summarize. Jupiter has 3 types of aurora. I've already discussed the moons. Here's Io. There's also Ganymede and Europa. Then there's the main auroral oval, okay, which is this feature here. This is a somewhat steady structure. At Earth, when we talk about the main auroral oval, it's variable, it's doing different things in response to the solar wind driver. This is very steady. So what this aurora is it is an internally driven aurora. Earth's aurora is externally driven by the solar wind. So think of Earth as the solar wind flowing by, stretching field lines, things snapping, and all sorts of activity happening in the polar cap. That's not the case here. So when you look at Jupiter's aurora, I naively thought, oh, well, that's just like Earth, you know. This represents a boundary between open and closed field lines, and everything in the polar cap is open to the solar wind. But no, it doesn't stop there. There's another type of aurora that you see in the polar cap here, and it's a variable aurora, and it's not clear what it's caused by. It's not an oval. It's patchy, it's sporadic. Sometimes you get bright flares. Sometimes there are little dark regions. And it's thought that perhaps this part of it is controlled by the solar wind. But it's controlled by the solar wind in a way that's kind of unlike Earth, because that's not what Earth's aurora looks like. This whole auroral region is filled in. So what I'm going to do now is play a video, and I'll do it a few times. What it is a compilation of observations from the Hubble Space Telescope, and it's going to be projected so that as if you're looking straight down from the pole. And part of the image is going to be black, and that's everything that you can't see that would be on the night side. Everything that contains the image of the baseline. And what I want you to observe is just look at the rich variability in this little play. Watch how things dance up here in the polar cap. This is the main oval, which is indicated by this red line. There are two lines here which basically bracket statistically where you see the main oval. This outer yellow line marks Eo's footprint. So every now and then you'll see the Io Aurora move by right there. Start that. And then there's all of this stuff in the polar cap, which is just dancing around. Now, as this image jumps around, that's because you're looking at different observing nights. But when you have a consecutive string of images here, they are roughly 2.5 minutes apart, just to give you a sense of the dynamics of this aurora. Huge flares, features that were there 1 minute aren't there 2.5 minutes later. Sometimes you see these filaments that seem to be aligned toward the sun. Right there. Okay, so a very dynamic thing. Let me just go back and let's look now at the analogous movie from Earth. Give you a sense of how different these aurora are. So typically what you see at Earth is if there's an event in the solar wind, so you get slammed with a shock or a coronal mass ejection or something, what happens on the night side is the aurora brightens significantly, as you see here, and it moves poleward, and it's very dynamic. But then it settles down into sort of a quiet state again. So what we're seeing here is the beginnings of the onset of a substorm. But rarely do you see any emission in the polar cap. It's very different than what we have at Jupiter. Okay, so let me just summarize this video once more. I'm going to show that movie one more time. So 3 types of aurora. Jupiter. The aurora associated with the moons, the main auroral oval, which is associated by the desire of the planet to hold on to its plasma from Io. This is not a solar wind-driven aurora, this is internally driven. And then this hodgepodge, this mishmash of auroral emission in the polar cap, which really has no analog at Earth. So what do you do? What do you do to really understand what's happening in the system? Data is sparse. We've sent a number of missions to Jupiter, starting in the 70s with Pioneer, 80s Voyager, Ulysses, Cassini, which went to Saturn, New Horizons, which is on its way to Pluto, went down the Magneto-tail. But these are all just threads of data. And what we really don't know about is we need information about what's happening in this polar region. It turns out that hopefully starting next year, we're going to launch the Juno spacecraft, which will be a polar orbiting spacecraft, which is going to explore these regions of Jupiter. It will be launched next year. It will arrive in 2016. So it's going to come in very close. Those of you who are familiar with the radiation belts of Earth, well, at Jupiter, it's even more severe. The electronics of the spacecraft could not handle flying through these regions of intense radiation, so in fact they have to dock underneath. So it tucks in very close to the planet and goes into a highly elliptical orbit. In doing so, it's going to cross these auroral regions, and we hope to get some really excellent data and try and shed some light on what is really happening in those polar caps so that we can understand the physics of the aurora of Jupiter in hopes of further understanding, better understanding what's happening at Earth. Thank you very much.